record this.
All right, so the first part of the lab deals with electrolytes. Electrolytes, you know, we have strong, weak, and non. And so what are the substances we're going to test? Now, there are two definitions for electrolyte properties. What are they? Two definitions for electrolyte properties. I really don't know because we're busy with the last test. But somebody know? Did somebody write it down off the board? It's very short. Yeah, that's the definition we're going to primarily stick with, the things that dissociate. What was the other definition? Conduct electricity. Now, the second definition is regardless whether it completely dissociates or not. You know, the definition of electrical conductivity just depends on how many ions are in solution. Electrical conductivity depends on three things. It depends on charge, mobility, and number. Now the number part is where a weak electrolyte can conduct electricity very well. You know, there are weak electrolytes that might conduct electricity very well because they're just present in high concentration. And so you might be deceived saying it's a strong electrolyte and think it completely dissociates. No, it's a strong electrolyte because it conducts electricity very well. But in reality, it's a weak electrolyte. It just has a high concentration. And so it depends on who you talk to, which definition you use. If you talk to somebody who works with electricity and batteries, then they don't care if it's strong, weak, or non in terms of dissociation. All they care about is, will it conduct enough electricity? Who cares what it is, right? But for us, we're using the other definition. And so you could have a strong electrolyte that barely conducts electricity. How? How can a strong electrolyte in fact, a strong electrolyte might not even conduct electricity at all. Why? Low concentration. Low concentration. There you go. And so what we're doing today is we're mixing it, and you got to keep track of these things, you know. And so the only way we can compare electrical conductivity, and a lot of you have already seen this lab before in Chem 4. This is a common lab with light bulb lab. A lot of you have seen this before, you know. And so the only way we can do this comparison is if we know the concentration. So, you know, we know the concentrations. We're going to keep the concentrations fairly high, and therefore we can make a relative judgment about dissociation. Okay. But everybody should know that there are two definitions for electrolytes. And electrical conductivity, you look more, you know, electricity and chemistry is very important, but it's covered primarily in Chem 1B. So anyway, just as an aside, you know, conductivity depends on three things: charge, on the species of conducting, the particle that conducts, for example, electron, times mobility times number. In symbols, it's sigma is equal to Z mu n. Now this equation is not in your book. You don't have to worry about it. But we worry about these things. It's a different, again, it's different than electrolyte. Well, let's take a look at some of the substances. What's the first substance we're going to test the electrical conductivity of? What's the first substance we're going to test the electrical conductivity of? Distilled water? DiH2O. DiH2O consists of H2O molecules. Do they have a charge? Do H2O molecules have a charge? No, the H2Os are neutral. Right? There's no charge. Do they have mobility? They have plenty of mobility. Are they present in large numbers? Yes. And so they have mobility, they have large numbers, but they have zero charge, so the conductivity is 0. We expect. Although, do you guys know about pH? Did you guys cover pH in Chem 4? Actually, has everybody covered pH? Then you guys know about auto-ionization of water. Pure water has a pH of 7, right? What does that mean, 7.00? Well, the pH means that there's a hydronium ion concentration. With a pH of 7.00, that means the hydronium ion concentration is equal to 1.0 times 10 to the minus 7 molar in pure water. Pure water is called neutral. Is it neutral because hydronium is acid? Why is pure water called neutral if there's acid present in water? There's also hydroxide, right? And it's called neutral because the hydroxide and the hydronium ion concentrations are balanced. They're equal to each other. And so this is a pH neutral. In acids, the hydronium ion concentration overwhelms the hydroxide, and in bases, it's the opposite. So where do these ions come from? In water. Well, it turns out that at 25 degrees C, the water molecules are moving. Right? And at 25 degrees C, what's your guess? Are all the water molecules moving at the exact same speed? Or do you think they're moving at different speeds? Because did you know that the temperature is a reflection of kinetic energy? You know what kinetic energy is? Kinetic energy? Actually, this is chapter 6. You can read about it in chapter 6, but since we're in chapter 6 now, let's talk about kinetic energy. Kinetic energy is the energy of motion. How many types of motion are there? How many types of motion? Well, there are lots of motions. There could be so many different motions, right? But what we want is a classification scheme where we can break it down into the smallest number of types, unique types. And I guess you could break it down into different categories, but if you think about the simplest motions, what are they? Can somebody tell me? If we have motions, what kinds of motions are there? Well, it turns out there are 3 types of motions. The first type is called translational motion. Translational motion is just going from point x1 to point x2 somewhere, or y2. It doesn't matter, in 3-dimensional space. Do that. The second type of motion is called vibrational motion. Vibrational motion happens with the bonds. And so for a water molecule can vibrate. That is, the bonds can go in and out like this, and the bonds can scissor towards each other like this. And then you have some kind of rocking type motion. And so if you look at how a water molecule moves within itself, you'll notice that actually there are, this is odd, there are just 3 ways. For other molecules, there are more ways it can vibrate. But we got vibrational motion. For example, like this. It's vibrating. This one out, this one in, different types, etc. And so that's one more. And there's one more type of motion that we deal with. You know what that is? It's called rotational motion. Rotational motion, the water molecules just rotate, or gas molecules rotate in space. It's rotational motion. There's a molecule just rotating. So those are the types of motion that we have. And you should know that temperature is a measure of, temperature, we'll just write it here. Kinetic energy is proportional. Temperature, actually we should say temperature is proportional to kinetic energy. Our book uses a symbol for kinetic energy, E sub K. E sub K, this you'll see in chapter 6. Kinetic energy. And so kinetic energy is the energy of motion. In physics, there's one other type of energy. Do you know that? What it is? Potential energy. Chemists are very interested in both kinetic energy and potential energy. When I talk about, when I talk about driving force for chemical reactions, do you know what? We're talking about energies, going from higher energy to lower energy, right? And so when I think about this, chemical reaction driving forces, I'm thinking in terms of potential energy, because the methane that's leaking out here is at room temperature. The oxygen in the air here is at room temperature. And so both of those are. Then I combust it. After I combust it, then I'll let it cool back down to room temperature, and everything will be back at room temperature after the heat's dispersed, right? And so what we do is we go from methane and oxygen to CO2 and water. Well, that's a change not in temperature. Although the temperature skyrockets, it's not going to stay up there forever. Eventually it will cool back down. And so eventually things will be back to the same temperature. And so when we're thinking about driving forces for chemical reactions, we always think in terms of potential energy. That's a high, like a stick of dynamite. A stick of dynamite, you don't want to keep in your back pocket, right? Because there's high, even though the temperature might be at room temperature or body temperature, there's high potential for explosion. Okay? Because the bonds are weak and we have potential to form stronger bonds. And so those are the 2 types of energy we are most interested in, potential energy over here. So kinetic energy, which is the energy of motion, and that's going to be related to temperature. And potential energy is going to be related to the bonds. How strong the bonds are. Weak bonds, unstable, right? High potential energy. Strong bonds, stable. This is for metathesis and acid base. For redox, we think in terms of also bonds and what? In redox, it's not just bonds. For metathesis, for sure, it's just, how strong those bonds are, acid base. For redox, we got to think in terms of somebody's got to know this. Not just the bonds, but also what? much this is the major factor. Yeah. Why don't you think about it? That way you might remember it much more if you figure it out yourself. That's a way to remember things. The way to remember things is to figure it out or find it, you know. Just find it. I talked about it before. I don't know how many times I talked about it, but I talked about maybe about 6 times. But this probably is just slipping your mind right now. But it'll be like that. Ring a bell. Well, anyway, when we talk about kinetic energy, let's say at 25 degrees C, you know, then we have to be careful because, oops, I'm running out of room here. Let's do it here. Erase this. It turns out that at 25 degrees C, not all of these water molecules have the same energy. Did you know that? You'd think, you know, this water is 25 degrees C anywhere you measure it. It's 25 degrees C. It's at thermal equilibrium. But some of the water molecules in here have low energy, some of them have high energy, and most of them will have some intermediate energy. And so what we see is we see a distribution of energies. And so the kinetic energy, more properly, is related to something else. The temperature is equal to some kind of constants times E bar K. You know what the bar represents? The average. And so this is called the average kinetic energy. And so if we have a 25 degrees C, what we're going to see is we're going to see a distribution of energies. This distribution of energies has a characteristic shape. You know, there are different shapes of distributions, and one shape is the bell curve, you know, the normal distribution of the Gaussian. This is not a bell-shaped curve. This curve is a little different. This curve looks something like this, where if I plot the population, or, you know, just the number, basically, versus the kinetic energy, EK here, the distribution looks like this. The distribution goes up, kind of peaks out, and then slowly kind of drops off. It's asymmetric. That is, this kind of like this tail on this side here. Actually, it should drop off more. Let's do something like that. This is what we call like a temperature or thermal distribution, or a Maxwell-Boltzmann type distribution. And so it has this kind of shape to it. When we look at this, where's the average? Well, the average is not at the peak here. You know, at the peak, this is the energy that that's most common right here, the highest population. But the average is going to be offset a little bit. And so the average is going to be around here. And so this is going to be a reflection of the temperature. And so this is, let's say, a room temperature. What happens if I increase the temperature? You know, if I increase the temperature, then the average kinetic energy should go up. The way the average kinetic energy goes up is, if it's the same population, then the area under the curve has to be the same. And so what we do is we thin out the lower energy and fatten up the higher energy. And so the average kinetic energy will be up here. This is E bar K at higher temperature. What happens if I lower the temperature? If I lower the temperature, then the average kinetic energy goes down, And so the population will thin out over here and increase down here, so we get something like this. This is at lower temperatures. Okay. We got to understand water, because water is so important in chemistry, right? We're going to talk about this again because we're going to hit pH later. But what we see is this. This is at 25 degrees C. Actually, you know, both of them are supposed to be at 25 degrees C. If I change the temperature, do you know what happens? If I change the temperature, does the pH change or the pH stay the same? If I change the temperature, will the pH change or will it stay the same? Well, if you know where pH comes from, then you'll know the answer to this. And so let's talk about where pH comes from. pH 7. pH 7 means that there's going to be hydronium and hydroxide, but where does the hydronium and hydroxide come from? Does anybody know where the hydronium and hydroxide come from in pure water? Where? And so the origin of this. The origin of this comes from this. Where this comes from is, let's take a look at this. Distribution. Call it the kinetic energy distribution. Describe the shape of the kinetic energy distribution curve to me. Well, it kind of looks like a normal Gaussian type distribution, normal distribution, except it has this higher energy tail here. Actually, let's drop this down. And so this is at 25 degrees C. And so at 25 degrees C, you have water molecules down here. These water molecules down here are kind of moving slowly. What types of motion do they possess? They possess, each water molecule possesses 3 types of motion. What are they? Translational, vibrational, and rotational. And so these water molecules have low translational, vibrational, and rotational energy. So they're just moving slow. That's it. Most of the water molecules in here are moving at this energy here. Most of them moving here. This curve is actually oversimplified. This curve is quite a bit oversimplified because, you know, translational motion, pretty much, you know, if it's moving from point x1 to point x2, it can move at pretty much any speed, right? And so if we start here at x1, go to x2, it could move slowly or it could move quickly or anything between those 2 speeds. But the funny thing is this. One of the funny things about vibrations is the vibrations, not every vibration is loud. You think it can vibrate slowly and it can vibrate quickly. But some vibrations are what we call forbidden vibrations. And it turns out that for water, there are only, I think, three allowed vibrations. You know, and that's it. And so water, when you're heating up a pot of water on the stove, a lot of that energy is wasted because a lot of that energy from the flame is not absorbed by the water. It has to be just the right energy to cause a certain vibration to occur, and then it'll absorb it. And so because of that, you know, the amount of energy that you use to heat up water in a stove versus the amount of energy you use to heat a cup of water in a microwave. In a microwave is tuned to hit the right energy. A microwave is tuned to hit the right energy for rotations of water molecules. And so that energy isn't wasted as much. And so, interestingly, not all vibrations and not all rotations are allowed. They're forbidden. This is called quantum mechanics, which is in chapter 7, or chapter 8. Chapter 8, which we're coming to. So we'll learn more about that then. It's like mass. Remember we were talking about continuous mass versus quantized mass. When we're dealing with, you know, crystals that were powder that we're weighing out on the balance, then we think of mass as being continuous, right? But when we get to very small quantities, then it's not continuous. Mass is, do you guys remember this from week 1? What did I call it? Mass is anyway, what should you start preparing for the final? Every week you should be preparing for the final. And so once in a while go back and look at the earlier stuff. Mass in reality is quantized, you know. And so this whole idea of forbidden masses and allowed masses, and forbidden vibrations and loud vibrations, forbidden rotation, shouldn't come as a surprise to something. Although, you know, the vibrations might, the rotations might. Well, anyway, the bulk of the water molecules will be here. And then, you know, they're going to be a small fraction of molecules in this red zone. You know what this red zone is representing? This red zone is representing very high kinetic energy. High enough kinetic energy to break bonds and react. This red zone represents maybe about 4 water molecules out of 1 billion. Last time I did the calculation, I need to redo the calculations to make sure. But something, you know, just roughly 4 out of 1 billion. Enough energy to break the bonds, the covalent bonds. You know, hydrogen-oxygen bonds about 400 kilojoules per mole or so. Breaks that bond if they collide. You know, if these water molecules have a lot of kinetic energy, they're always moving and always colliding. If you get 2 of these red ones that collide, what's going to happen? You're breaking bonds. When you break bonds, well, 2 things can happen after you break the bonds. 1, everything can be put back together as it was before. And so you break the bonds and it reforms water. 2, you break the bonds and it forms a different product. A chemical reaction occurs. Now, what is that chemical reaction? Well, the chemical reaction is this. The chemical reaction is called autoionization, or self-reaction of water. One water acts as the acid, the other acts as the base. And so one H2O liquid collides with another H2O liquid. This is going to produce H3O plus and hydroxide. And so we have the acid, which is proton donor, the base, which is the proton acceptor. So we'll call this the base, we'll call this the acid. But does this reaction have a driving force? Does this reaction have a driving force? Well, what do we do when we look for driving forces? Yeah, more stable. So we just compare. Going in the backwards direction, what's the acid, what's the base? This is tricky because, you know, hydroxide is not always the base. Hydroxide can sometimes be an acid. This is amphoteric. In this case, hydronium can only be an acid, but sometimes you get fooled. I can fool you sometimes. Some people I can fool. into thinking hydroxide's always a base, but it's not always a base. You know. And so don't automatically think. What we do is we look in the backwards direction, who's losing, who's gaining. You know, it's the same habit. You know, in Chem 1B, I fool some people into thinking hydrogen peroxide is always an oxidizer. No, hydrogen peroxide can be a reducer too. They always think of it as an oxidizer because it's one of the most powerful oxidizers. It's an extremely weak reducer. But still, if you have an even more powerful oxidizer than hydrogen peroxide, then hydrogen peroxide will be the reducer. But who's losing, who's gaining, going in the reverse direction? So just look and see.
Pure water.
Yeah, going backwards. What's this? The acid or the base?
Acid.
This? The base, because this one loses to form H2O, this one gains to form H2O. So that's how we figure it out. We don't figure it out because, oh, I've memorized hydroxide's a base. If you did it that way, then you're going to be wrong sometimes. Okay. Hydronium's always an acid. It can't be a base. And so that one you could have done from memorizing. Which one's stronger? This one, do we need the acid chart for? I hope not. Which one's stronger? That should be obvious. So what do we say? What do we say? We say no reaction, right? No reaction. But, you know, barium sulfate is insoluble, right? Does that mean nothing will dissolve? Absolutely nothing will dissolve. Barium, no. No. What happens is you have the surface of barium sulfate here. Are all the water molecules moving at the same speed? No. What if a high energy water molecule strikes the surface of barium sulfate and knocks an ion off? Then some of it just dissolved. Are there high energy water molecules present at 25 degrees C? Yeah, just very small number, a tiny amount. And so we say no reaction here, but that's not true, is it? No, there is a tiny, tiny bit of reaction that occurs. In Chem 1B, we're going to look at the details of this. In Chem 1A, we just call this no reaction, except for this particular one. For this particular one, we're going to say a tiny, tiny bit will react. And so normally we say no, but here we're going to represent it like this. Maybe we'll draw a big arrow backwards and a tiny arrow forward, saying no. And the reason is you know, even though there's no driving force for this, even though we're forming unstable, highly unstable products, the reason for this is, it's probably hard to get because I went through it so fast yesterday, but we got to look at two things in a chemical reaction. We look at the thermodynamics and we look at the thermodynamics and we look at the we talked about it in terms of graphite. That was just yesterday.
Stability.
Not the stability. Do you see how rapidly memory fades? Well, that's thermodynamics. So we look at thermodynamics, the strength of the bonds, and we look at not the structure. I didn't spend much time on it, so maybe it didn't register. If it doesn't register, then obviously it's in your memory. Graphite versus diamond. Graphite versus diamond is the classic case of thermodynamics versus kinetics. That's it. Kinetic. In other words, can we stop these water molecules from colliding? Is there any way we could stop the water molecules from colliding? No. You know, we can't put some wall between the water molecules. If they're going to collide, they're going to collide, right? And so what's going to happen is these two species are highly reactive, right? They're highly reactive, and what's going to happen is they're going to revert back to pure water, because if you have strong acid, hydronium, and strong base, hydroxide, that's a very strong driving force to form water. And so these guys don't last very long. And if they don't last very long, then why isn't it completely depleted and we end up with none? The reason is we cannot stop the collisions. And so immediately after these guys revert back to water, what's going to happen? Well, two more water molecules are going to collide and reform hydronium and hydroxide. Have you ever heard of a dynamic equilibrium? You should have, but maybe forgot. What is a dynamic equilibrium? Dynamic equilibrium is a case where we have the rate in one direction exactly equal the rate in the opposite direction. And so what we do is we reach a stable state, a steady state. And the same thing's going to happen here. What's going to happen is the rate of the consumption will equal the rate of formation and will reach a steady state. The steady state here is this: 10 to the minus 7 molar, 10 to the minus 7 molar, giving us a pH of 7. But the reaction's constantly occurring. It never stops. That's a dynamic equilibrium. And so we're always going to have this here present in water. And so, okay, we have charge. Hydronium is +1, hydroxide's -1. We have mobility. What are we lacking in pure water? What are we lacking? In this pure water right now, there's hydronium and hydroxide. I'm going to ask you, oh, that's not really pure. That's dry. Distilled water is expensive. It takes a lot of energy to make it. So in this is distilled water. It's as pure as you're going to get, right? Are there ions present? Yes. There's hydronium and hydroxide present in here. Will this conduct electricity? Well, if there's ions present, it should conduct electricity, right? The electrodes are very dirty. Will it conduct electricity? It should. If there are ions present, it should, shouldn't it, conduct electricity? And so what we have here is, if you haven't seen this, I think, has everybody seen this? Has anyone not seen this? Everyone's seen this, right? This is why I'm spending more time on this stuff that we're going to encounter later, so you hear more than once. Water and electricity don't mix, right? Water is very dangerous to have open electrodes like this connected to the electrical outlet and have water present, right? You're going to get electrocuted because water conducts electricity, right? So we can test this. So right now this is not going to conduct because there's nothing connecting these two electrodes. I need a piece of wire or something to connect them. But now I'm going to use some water to connect the circuit. And let's see how it conducts. So hopefully I get electrocuted. Okay, maybe there's something wrong with my light bulbs, because do you see any light there? No. I don't. Do you see any light there? No, I don't either. Let me check something. Make sure this is working. What's the difference between deionized water and distilled water? This is not working. Try a different plug here. Now that's working. Oh, this is salt water here. Salt water definitely conducts electricity. Conducts electricity very well. Let's rinse these off. Waste beaker. So let's wash the salt water off the electrodes here. I'm going to use some distilled water now. I don't want to use too much because I'm going to save it later. Do you see any? No. And so distilled water does not conduct electricity. Distilled water is known as an insulator. It's an insulator because you know how they define insulators, semiconductors, and conductors? They define it by a number, and the number is how much it conducts. The number is this. It's sigma. This is actually a number. And they have breakdowns. If the sigma is over this, we call it a semiconductor. If it's over this, we call it a metallic conductor. If it's under this, we call it a insulator. Those are kind of arbitrary cutoffs. The sigma is given in units that are called Siemens after the semiconductor company. It's not after the semiconductor, it's after the scientist named Siemens. But water is an insulator. In fact, if you measure the resistance of water, it has mega ohm resistance. This is how we test water quality. If you use a lot of distilled or deionized water, you test its resistance. You need, like some number of mega ohms, like 5 mega ohms, 10 mega ohms, 15 mega ohms of resistance. Then you know it's a very good, very pure water sample in terms of ions. Okay. And so water is considered an insulator. It's not conducting electricity. But why should it be an insulator? Because there are a steady state of hydronium and hydroxide ions present. And hydronium and hydroxide ions should conduct electricity. Water molecules themselves don't conduct electricity because there's no charge. One of these electrodes is positive, the other is negative. And what we need to do, actually it's oscillating, but what we need to do is we need to conduct a charge. And so why doesn't pure water, distilled water, conduct electricity? Somebody tell me why. Well, it's an insulator. Well, tell me why is it an insulator? Well, it doesn't conduct electricity. Well, why doesn't it conduct electricity? Because it has resistance, megaohm resistance. Why does it have megaohm resistance? This is an insulator. Well, you know, tell me why. Tell me why in more scientific terms, you know? I don't want, that's the typical answer I get. Test. That's an insulator. It doesn't tell me anything.
It's not enough concentration of ions.
Yes. This is a scientist would say, they put it in numbers. There's charge, there's mobility, but there's very low numbers of these ions. Not enough to sustain much of a current. And so in theory, yes, there's a little bit of conduction, but not enough to conduct anything, really. And so we call it, there's got to be a break point. It's like solubility. You know, so everything dissolves. It's just the degree to which it dissolves. And so if it's below a certain cutoff, we call it insoluble. But that doesn't mean none of it will dissolve. Tiny bit does dissolve. Okay. All right, so DI water, when we think about this is, you know, even though this sits here, you know, do you see much kinetic energy with these electrodes? No, I don't see any motion, really. There is some kinetic energy. The kinetic energy, you know, the metal atoms are vibrating in here. But I don't really see much. But I see high potential energy. There's very high potential energy because, you know, there's a pretty big charge difference between these. One of these has a lot of electrons. The other has very little electrons. It's imbalanced, right? That's high potential energy. Now, potential energy is measured in terms of voltage here. The higher the volts, the larger the imbalance. We use voltages a lot for lots of different things. And it's just charge imbalance. This is why electrical neutrality, when you guys are doing nomenclature, you got to make sure the cations balance the anions. Otherwise, you create a huge voltage. It's like static electricity. It becomes extremely unstable due to the high potential energy. Well, in this lab, what we're going to say is this. What is it asking for as far as that data entry? It's asking for, just read the major species in solution. What is the major species in solution, you say? Well, if you were inventory water, what is the major species in solution for the inventory? You know, when we're doing inventories for redox reactions, did I consider the hydronium and hydroxide that occurs in autoionization? No, because the concentrations are just way too small, so we ignore them. This is just not enough to do much reaction. The major species will just be water molecules. Then what does it ask for next? Minor species in solution. What are the minor species? Yeah, the minor species would be hydronium and hydroxide. But these are minimal. As far as electrical conductivity goes, they're negligible. As far as a lot of chemical reactions go, we don't factor that in because it's so minor, extremely minor. In Chem 1B, you'll do a lot more with this. Okay, what else is it asked for? Electrolyte type would be, we call water a non-electrolyte. Non-electrolytes do not dissociate or hydrolyze. We know that's not 100% true. It does dissociate, but not to any significant extent. Okay, enough to cause pH, and the pH is very important. All right, what's next on the list? Tap water. All right, tap water, on the other hand, what do you think? Tap water conducts electricity. You see the bulb? It lit up. This is tap water. Why does tap water conduct electricity? Minerals, yeah. Minerals, salts, that kind of stuff. It's just ions are present. What's next? Sodium chloride, salt water. Does tap water taste salty? No, but you can taste the minerals. The minerals give it flavor. But salt water, this is 1 molar, is going to taste very salty. Let's take a look here. You see that? Salt water is an excellent conductor. Unless, you know, what happens if I dilute the salt water? If I dilute this salt water, this is 1 molar. 1 molar conducts electricity as good as copper wire. Why does salt water conduct electricity so well? Oops. It's bad. I don't know what. It's kind of bad connection. Here. Kind of bad. I'm going to put this on a ring stand, but I don't have a ring stand. Well, why does salt water conduct? Well, this is sodium chloride. Sodium chloride is a strong electrolyte. Strong electrolytes dissociate into sodium ions and chloride ions. And if we have a high enough number of them, it's going to conduct electricity very well. And so that's salt water. Salt water we call a strong, weak, or non-electrolyte. Strong. And so strong electrolytes should conduct electricity, but this is salt water too, right? This is salt water, but what happened to the bulb? Now it looks like tap water because I diluted it. And so salt water might not, you know, even though we call sodium chloride a strong electrolyte, it might not conduct electricity at all depending on its concentration. And so this is why we always think in terms of 2 definitions. Because just because we have salt water doesn't mean it's going to be a good conductor of electricity. It should be at high enough concentration. Okay. All right, what's next? Do 1 more and then we'll take a break. What? Solid sodium chloride? Okay. This is reagent grade sodium chloride. This is sodium chloride you buy from the chemical company. This stuff is much more expensive than the stuff you get at the supermarket. But it's still, this is not high purity stuff. This looks like well, maybe 99.5% pure. It was pure enough. I need a small beaker. All right, solid sodium chloride. Will it conduct electricity? Why not? Good. Good. The answer I was looking for is because there's no mobility. No mobility. There are plenty of charges, plenty of ions, but just no mobility. How can we get some mobility? It's not going to conduct. Although you know that sodium chloride, right below its melting point, it's still solid salt. Right below its melting point, like I think about 3 degrees below or 1 degree below its melting point, will start to conduct electricity as good as copper metal. That's solid salt. It melts at a very high temperature. And so how can I get some mobility in there? I can free up the ions. This is what we did with, remember sulfate? Sulfate was locked in an ionic lattice, and we freed it up by doing what? Let's use this. Well, you'll tell me about it in the report. So, just add some water to this. There we go. We have mobility now. Lines are free. Okay. That's conducting as good as copper metal there. Copper metal is the standard we use for high conductivity. There are things that conduct better than copper metal. Superconductors, etc. But copper is pretty much the standard for high conductivity. All right, let's take a break here, and then we'll continue.